All right. Hello and welcome back. Good evening. Could you please give me a +1 if you can hear me, okay? And if you can see my screen. Okay, perfect. Thank you. So today's miniature is about the clubs of Odd Town. This is essentially a combinatorial question about a set system. And in fact, this is one of those miniatures which makes me wonder about whether there is, in fact, a non-linear algebraic way of looking at the fact that we are going to prove, because the linear algebraic proof really springs out of nowhere, especially if you aren't already familiar with this style of argument. And it almost feels like this problem was designed as a very cute advertisement for this method, which sometimes goes by the name dimensionality argument, so the dimensionality method for arguing upper bounds. So I haven't found a proof that's purely combinatorial or from first principles. I'd be really curious about if there is one. So if anybody wants to give that a shot, I think that would be great. But with that said, let's get to the actual problem that we want to focus on. So this is about a town called Odd Town. We will see why. We have N citizens who live in Odd Town, and they're pretty jobless as citizens go. And they spend most of their time forming clubs, hanging out. And this makes the city's administration kind of worried about all the frivolous time that is being spent. So they want to introduce some regulations to cut down on the number of clubs. From our point of view, a club is just a subset of people. So assume that the N citizens are ID'd by the natural numbers 1 through N. Any non-empty subset of N is basically a club. And let's assume that we are thinking of collections that are not multisets, which is to say that the same set of people can refer to themselves as two different clubs, although that's possible and even plausible in the real world. Maybe the exact same set of people share more than one interest. But as far as our discussions go, we are really going to think of clubs as distinct subsets. For certain questions that we frame around this distinction won't even matter, because the kind of constraints that we are going to impose in the system will rule out repeated clubs anyway. But in some other variants of this problem, they're not automatically ruled out. So I thought I'd just make this explicit from the get-go. So we're looking at distinct subsets of people. If you have no constraints, as was the case in the beginning with Odd Town, you can form exponentially many clubs. So in fact, I should say 2 to the n minus 1, because I already said you can't have the empty club. But if you want to have a fantasy situation where you allow for the null club, which is a cool club which doesn't have any members, it's super exclusive, then you have 2 to the n clubs. So that's the situation that the administration finds itself in. So they want to cut down on the number of clubs. And the story goes that they declared the following regulations. They said, well, each club can only have an odd number of members. And that's where the name Odd Town comes from, as you might have guessed. But they also further imposed that every pair of clubs must have an even number of members in common. And we want to think about, to what extent does this bring the total number of clubs under control? So as a warm-up, let's think of these constraints one at a time. So what if we only constrained the clubs to have odd size? How many clubs can we form if this was the only rule in play? I will watch out in the chat for any suggestions. Okay, that's 2 to the n minus 1, precisely, because the number of odd subsets of 1 to n is equal to the number of even subsets of 1 to n. And you can see this by a matching argument, something that you might also think of as a bijection argument. If n is odd, then any odd subset will have a complement which is even sized, right? For example, if n was 5 and I pull out a subset of size 3, its complement is going to be a subset of size 2. So matching a set to its complement establishes a bijection between the collection of all odd-sized subsets and all even-sized subsets, which means that the number of odd-sized subsets must be equal to the number of even-sized subsets. However, every subset is either odd or even. So you're going to only have, well, you're going to have half the total number of subsets being odd. And this argument works well when you have n being odd, but when n is even, you can basically single out somebody and do a case analysis based on sets that contain that element and don't contain that element. And in both of these universes, you can essentially repeat this argument to get to this claim. So that's a fairly straightforward thing to show, and I won't actually get into any further details, but hopefully you're convinced or you know it already. So either way, moving on, what if we only insisted that every pair of clubs must have an even number of members in common? This one's maybe a little less obvious, but can you still form lots of clubs? So notice that if we only had the first rule in play, we still have exponentially many clubs. I mean, you could say that we cut down the total number of possible clubs by half, which is, well, significant, but it's still an exponential number of clubs, which feels like too many. So what if we only have the second constraint where we say every two clubs must have an even number of members in common? Can we still create somehow exponentially many clubs? Is that still possible? Can we think of examples? Yes, we do allow 0 to be even. So you could have clubs that are fully disjoint, and that would be fair play. Yeah. Okay, how do we have 2 to the n minus 1 for the second situation?
Ma'am, if we found the clubs with only even members, then any two intersection will have only even number of members.
Okay, so we only form clubs with even numbered people. Is that the suggestion? Or are you saying that we only have clubs of even size? Is that the point? Well, you could have two clubs that have even size, but an odd intersection. That's still possible, right? So for example, you could have a club that has 1 and 2, and then you could have another one that's 2 and 3. And although they both have even size on their own, they overlap at just the number 2. So you could still have odd intersections while having even size. So if we have even sized clubs, that does not guarantee even sized intersections. So that's going to be a problem. 2 raised to n minus 2, make 1 and 2 common to all. So Jagdish, I think that's also a good starting point. But again, the problem is that if you have two clubs that have, I'm assuming that you're taking all possible subsets of the remaining n minus 2 people. And yeah, so if you have two sets that overlap at an odd number of elements, that number just goes up by 2. And that does not change its parity. So it's still going to be odd. So in case anyone found that confusing, you could think of, well, you have, let's say, the clubs 3, 4, and 4, 5, which you would have if you take all possible subsets of 3 to n. And 3, 4, and 4, 5 overlap only at 4, so they have an intersection of size 1. But then if you add 1, 2 to both of these clubs, then the intersection size goes up from 1 to 3 and doesn't make it even. So unfortunately, we are not multiplying everything by 2. That would have worked, but we are only adding 2. So that preserves parity. All right, so maybe here's a hint. What if we assumed that Odd Town consists of n by 2 couples? Let's assume for now that n is even so that we don't have to do anything weird to have n by 2 couples. And yes, so Jagdish, 2 to the n by 2 is sort of what I was going for as well. Do you want to describe your example maybe? All right, it's a good guess. So that's indeed what we will be able to show, that you can get 2 to the n by 2 clubs. So imagine that odd town consists of n by 2 couples, assuming for now that n is even. And let's say that our couples are really, really like-minded, so they only go to the same set of clubs together. Thinking of couples as sort of atomic units, can you think of a way of forming 2 to the n by 2 clubs, which respect the constraint that every pair of them must have an even number of members in common? So also, if whatever you have in mind is too tedious to write out, please feel free to unmute yourself.
Ma'am, what is the question?
Right, the question is, can we construct a collection of 2 to the n by 2 clubs, which have the property that every pair of them overlap at an even number of members? So just stepping back for a moment, what we said was that the administration introduced these 2 constraints on how clubs can be formed. And I want to sort of justify that there are these 2 rules that are being imposed simultaneously by saying that if you only had one of these rules at play and not the other one, then you can still form lots and lots of clubs. In particular, you can form exponentially many clubs, which is why perhaps the administration felt that it was important to impose both of these rules together. So, all right. So I think Jagdish has a suggestion which basically says either pick a couple or don't pick a couple. When we said that we will pair up everybody in odd town and think of the pairs as a single unit. So think of basically all possible ways of picking subsets of couples instead of individuals, right? There are n by 2 couples, so there are 2 to the n by 2 ways of forming subsets of couples. If you want to be really picky, you can throw in a -1 to avoid the situation when you're not picking anybody at all. But basically, roughly 2 to the n by 2 choices that way. And now notice that if you pick any pair of clubs, the number of common elements can also be thought of as a collection of couples, because couples attend or choose to not attend a club together. So the number of people that attend are present together in a pair of clubs is also a collection of pairs, making them even. So I'm not sure, but if that made sense to you, could you give me a +1 in the chat to say that we want to basically, the claim is that we can form 2 to the n by 2 clubs, give or take 1. Basically, take 1 if you don't want the empty club, with this idea that you divide the population of odd town into couples. Okay, if we want to make that a little more explicit, imagine that odd town has 10 people. So think of 1, 2 as a single unit. Think of that as a pair. Think of 3, 4 as a pair. 5, 6 as a pair. 7, 8 as a pair. And 9, 10 as a pair. Now take all possible, think of the space of all subsets of 1 to 5, right? So if you give me, for example, the subset 3 and 5, I'm going to take the third pair, which was 5 and 6, and the fifth pair, which was 9 and 10. And I'm going to say that that's my club. Right. So for every subset of 1 to 5, I can pick a collection of pairs and call that my club. And now if you take any 2 clubs, they only overlap at pairs, which ensures that the intersections, the pairwise intersections, are even. So did that sort of make sense? All right, wonderful. So just in case that wasn't very coherent, I promise you it's an idea that does work. So maybe maybe that's something that you can come back to when you have a chance in a bit. All of this was to say that if you apply these constraints just on their own, then you still have a lot of clubs. So let's see what happens when you apply both of these constraints together. So these are the rules now. You have to form a collection of sets which all have odd size and pairwise even intersections. Now, can you think of examples where you still have lots and lots of clubs, even though you conform to both of these rules? Notice that in the examples that we had before, when we had lots of clubs, we were respecting one of the rules and violating the other one. So for instance, with the odd number of members, we said, let's take all odd-sized subsets. But of course, odd-sized subsets do have odd-sized intersections often. So we were in violation of the second rule. And then when we did this thing about pairing up people and taking all possible subsets, well, then all of our subsets actually had even size. So we were blatantly violating the first requirement. So our previous examples will definitely not work. But does anybody have an example of an any-sized collection? I'm not demanding now that we have a very large collection, but just any example of a collection of clubs that satisfy both of these properties, a collection of subsets, if you prefer that terminology. Okay, so Manmohan suggests that we take only singletons, which is indeed the first example that I had. So singletons are a really clean example because, well, of course, maybe not the nicest example because these are really lonely clubs to be in. Every club just has the one member. So the ith club just has the member I. But it does satisfy both of those requirements because pairwise intersections are empty, so the size is 0, which is even, and the individual sizes, of course, are 1, so that's odd. It's also odd in real life to have clubs that only have one member each. But moving on from that, it's interesting to think of other examples, but you can play around with this. It turns out that you cannot really improve on this simple example in terms of size, in terms of the number of clubs that you can form. So I do have another example which was similar to what was said before in the chat, which was to have a common pair, a pair that's common to every club to ensure even intersections. So in the second example, 1, 2 are all over the place. And then you can think about how you want to develop the rest of it. So what I have done is the simple thing of continuing with singletons beyond 1, 2. But you could spread this out and combine people in other ways as well, as long as you keep in mind that the sizes have to still be odd. And in fact, here I'm even falling short of n. So I don't even have n clubs in this second example. So in fact, the collection of all collections that have n sets that satisfy both of these rules also has some nice combinatorial properties, but that's a little out of scope for us, so we won't go there. So we just have two examples, both of which are valid and only one of which is maximal. And that brings us to the surprising result, which says that if you are constrained by both of these rules simultaneously, then you cannot form more than n clubs. Okay. So please let me know if the setting and the claim, if both of these things are clear, that this is what we want to prove, because from here, what we're going to do is actually try and prove this claim. Or just let me know if you have any questions, if there's anything that's unclear. Okay, thank you, Aditi. I'm not hearing any complaints, so I'm assuming that this is clear so far. All right, so the technique that we are going to use to show this upper bound is going to involve mapping sets that form our clubs to appropriate elements of a vector space. So the idea is to come up with a general way of establishing the relationship between subsets of n and some vectors in some appropriate vector space. And the hope is that this mapping will have the following property: that if you have a collection of sets which satisfy both of these rules, then the map takes them to a linearly independent collection of vectors. And notice that if we are able to come up with such a map, then we're basically done if these vectors live in a n-dimensional vector space. Okay, so if we are able to map these sets to vectors that sit inside a vector space of dimension n, and the map has this property that it maps valid collections to linearly independent vectors, then the reason we are in business is that you couldn't have more than n sets that satisfy both of these rules, because if you did, then they would map to a collection of more than n vectors, which are linearly independent in a vector space of dimension n. But that's a contradiction, because you cannot have more than dimension many vectors that are linearly independent. So that's the plan of action. And it sounds great on paper. The main question is, can we actually come up with such a map? And what is this vector space that we want to map these sets to? Well, all right. So let me just go ahead and tell you what the mapping is. So I have this array of boxes here, which are supposed to represent my people of Odd Town. And here, the green boxes represent a set. So in this case, reading of the boxes from left to right is 1, 2, 3, and so on. This represents the set 1, 2, 4, 5, and 7. Okay, hopefully that notation is clear. And now what I want to do is I want to map this to a vector with 10 coordinates over F2, where F2 is the field with 2 elements, addition modulo 2 being the operation. So the elements of my field are 0 and 1. And the operation is basically 0 plus 0 is 0, 0 plus 1 and 1 plus 0 are both 1. And 1 plus 1 is 0 because we have addition mod 2. Okay. And the way I'm going to perform the mapping is essentially to say that let's represent this set as what you might have seen as the characteristic vector of that set. If you have not heard that term before, don't worry about it. What it basically looks like is we are going to think of giving the set a signature where we give 1s to all the coordinates whose corresponding labels belong to the set and 0 if they don't belong to the set. So this is what the vector corresponding to this set looks like. Okay, so we have the 1s sitting in those coordinates, which are basically elements of the set, and 0s everywhere else. So if you look at the set, hopefully you can see what vector it maps to. But if I only give you the vector, you can hopefully also reconstruct the set by simply reading off the indices of the 1s. Okay, so just to make sure that we are on the same page, can somebody tell me the vector corresponding to the set 1, 3, 5, 6, 7? Hopefully that's a different one from what we have on the picture. Yes, I think it's different. I'm just going to give this a minute here because this mapping is basically the heart of the whole argument. So I just want to be sure that the mapping itself is clear. Okay, so we seem to be in agreement on this. We have 1, 0, 1, 0, 1, 1, 0, 0. And hopefully I don't have a typo here. So let me color code that so it's easier to see. So that's exactly the map that we have. So thank you everyone for responding. So indeed, this is going to be okay. So I think we're pretty much there. So thanks everyone in the chat. So let's look at this map and see if it has the properties that we desire. First, I said we want to land in a vector space of dimension n. This is indeed true because these are basically vectors with n coordinates. The vectors sitting in F2n. And you can just look at the standard basis to realize that this is an n-dimensional vector space. So we have the correct destination. All that we need to argue is that if you're coming from a collection of sets that respect these two rules, then we have landed with a collection of vectors. We've landed up with a collection of vectors that are linearly independent in the target space. And I think in the book, the proof is done using matrix notation. And as you can see, I'm a little cramped for space here. So I'm going to do a more pedestrian proof of linear independence, just basically going by the definition. So what I'm going to say is look at this expression here. If you have a linear combination of all of these vectors, which goes to 0, then that cannot possibly be a non-trivial linear combination. All the alphas must also be 0. So if I can argue that for you, then these vectors will indeed turn out to be linearly independent. And just to back up a bit, let's make sure that we are on the same page about what these vectors are. These vectors are what our linear map from, maybe I shouldn't call it a linear map, but let me just say the map that we described just now, these are the vectors that we are transported to from any hypothetical club system that respects the odd down rules. So you give me a collection of clubs and you say, okay, look, these all have odd size and these all have pairwise even intersections. And I'm going to say, okay, let me take your clubs and apply the map on each of them. And I will end up with a collection of vectors. So these are those vectors, right? So V1 is the map, let me call it F, applied to S1. V2 is the map applied to S2, and so on, right? So these are the vectors, and these are the vectors whose linear independence I want to establish. So I just need to demonstrate here that all the alpha i's are 0. And I'm going to do that by multiplying throughout with Vi. To show that alpha is 0, I'm going to multiply both sides by Vi. And I'm a bit sloppy with the notation on the right-hand side. That's just the 0 vector. And when you multiply the 0 vector by Vi, you again get the 0 vector. But more interestingly, let's look at what's happening on the left-hand side. So what can we say about this term? What is Vi inner product Vi? Remember that all clubs have odd size, and I think we already have a response. It's indeed 1, because when you take the product of a vector with itself, and this is happening over F2, and these vectors have an odd number of 1s, basically what you're recording is the parity of the total number of 1s in that vector. Okay, so you take this vector, multiply it out by itself. So the number of 1s that's there is basically the size of the set that we are coming from. So I hope that that's clear. We are essentially counting the parity of the size of the set, and that's going to be 1, because according to the first rule of odd down, all sets must have odd size. So I hope that that's clear. And let's move on to Vi times Vj, where I is not equal to j. What do you think that product will work out to? Okay, we have a claim that it's going to be 0, and hopefully that's clear as well. This problem was really set up for this to happen. That's basically the parity of the number of elements common to both Si and Sj. And indeed, by the second rule of odd down, we know that we are going to capture an even number of 1s. And I hope that it's clear why it's the intersection, because those are the only indices that will survive when you take the product. When you take the product, you have to be a 1 at the same place in both vectors. And that means a person that belongs to both the clubs, that's going to account for the 1s in the product. All right. So that's the parity of the intersection. But of course, by the rules of odd down, we know that the sizes of the sets are odd. So the size of Si mod 2 is 1, and the intersections are even. So the parity of Si intersection Sj is 0. And that's pretty much it. So the only surviving term is alpha I. That's what you have on the left-hand side, and on the right-hand side, we have 0. And that's just in time. So, okay, let me just comment that you might now start thinking about, well, what's special about the odd even constraint? Can we impose other constraints like, say, even size sets with even sized intersections, or maybe even size sets with odd sized intersections, or odd size sets with odd sized intersections? So those are all prompts for discussion for this miniature, and that's a good conversation to carry on in the forums. I think I do have some additional slides arguing the case for Eventown. I don't think this is covered in the miniature, but there are some, there is a nice proof around Eventown, but out of respect for time, I'm not going to get into that part of the argument right now. However, I'll be happy to talk more about it at the forums, or if anybody has any questions, this would be a good time to address them. Any questions or comments?
So why do you need the F2N at all?
Okay, do you mean couldn't we just do this over Rn? Is that the question?
No. So you take the inner product, you find one term is odd.
Right.
And then the remaining terms are even.
Correct.
And you want the 0.
Correct.
So you just go mod 2 on this, and I would think people understand mod 2 a bit better than F2 being a field and so on. And so you really don't need to set up a formal field property, right? All that you're doing is a parity argument.
I am only doing a parity argument. That is true. But I do need, I do need to say that I do need to exploit the dimensionality of the vector space to be able to say that, well, the linear independence gives me that T is at most n. Isn't that true?
Mm-hmm. So I don't know. I think you should try and see what happens with alphas actually.
Sure. Okay. So I mean, I'm assuming that what you are suggesting is that we needn't have taken the field to be F2. Is that the point? That at this point?
No. Can you do an argument without? I think parity is something, for example, all high school students will understand.
Correct.
Right?
Correct.
So can we actually avoid bringing in F2N?
Right.
And then somehow arguing just based on parity is the question.
Right. But we will need the vector space structure still for the argument to go through, right? Or are you saying?
No, you require vector space.
Correct.
But this vector space is on. So what is this vector space on? Even the vector space does not necessarily require a field structure.
Correct. That's true. I mean, we do need it to be over some sort of a field, don't we? Because just even to describe the vector operations, I mean, we talk about, well, I don't know. It typically
let's think about it. I think.
Yeah. Maybe a good question to take offline. Yes, so like I think Jagdish is saying in the chat as well, what I would like to see is a proof that is just purely combinatorial, and I'm also not aware of one. If we map this to Rn, then I think the arguments was plausible, I suppose, but it doesn't come through that nicely because Rn will not capture parity. I'm not even sure if the vectors end up being linearly independent in Rn. So yeah. So yeah, I mean, making this argument devoid of the F2 notation and just relying on parity, I think that's a language improvement that can probably be worked out. And let me think about that and try to get back to you offline. Yeah. All right. Are there any other remarks? Right. So parity is certainly a more, I guess, a more self-contained thing that doesn't Well, I mean, I'm tempted to say that the operations in F2 are basically parity based, but there's probably a little bit more cognitive load in carrying both of those notations or both of those notions simultaneously. But hopefully the mechanics of the proof were convincing. And Mohan is asking, where does the not more than n come into the picture? Well, that's the high level setup where we said that if you manage to map a collection of sets to a vector space, where you ensure that if this collection has the properties that it's supposed to have, then it maps to linearly independent vectors in that vector space, then the number of things you can have in this collection is bounded by the dimension of the vector space that you take them to. And in this case, we managed to map everything to a vector space whose dimension is just n. And these vectors indeed turned out to be linearly independent. So you cannot have more than n sets simply because you cannot have more than n vectors that are linearly independent in this space. So I hope that made sense. So in short, the not more than n comes from the dimension of the vector space, and that is why this is called a dimensionality argument even. Right, so Joel, that's a great point too. Like we could work over larger fields FQ, and I think some people have asked questions about what happens if instead of talking about odd and even, which you can think of as constraints being 0 mod 2 and 1 mod 2, you could generalize to P mod Q kind of constraints, right? But for handling those variations of the problem, I think you do indeed go to fields which are like FQ. I think those fields are well defined for prime powers, I think. And so that probably constrains a little bit what you can work with, but there is definitely some literature along those lines. So I'll try to pull up some pointers as we go offline. But the couple of discussion prompts that are there indeed inquire about what happens when you go beyond mod 2. So that's definitely a nice and natural direction to take this in. All right, so I think we are a little over 5 minutes over time. I'm sorry that we pushed this a little over the edge today. So I'm going to stop here as far as the official session is concerned from the point of view of the recording. So let me just close the recording.